All right, for today's lesson, we are going to be talking a little bit more about unit vectors. We introduced unit vectors when we introduced vectors in general, and we did talk a little bit about what unit vectors are, but we're going to be applying more of our knowledge of vectors today. So first, let's just remind ourselves what a unit vector is. A unit vector is a vector with magnitude 1. So for example, if you have this vector here, with components 1, 3, we know it's not a unit vector because we can find the magnitude of this vector, and the magnitude is square root of 1 squared plus 3 squared, which is square root of 10, which is not equal to 1. So that's how we can tell it's not a unit vector. On the other hand, if you have vector v equaling 1 over root 2, comma, negative 1 over root 2, we know that this is a unit vector, because if we were to square each of those, add them together, and then take the square root, that would be equal to, well, that's 1/2 plus 1/2 under the square root. Add those together, we have the square root of 1, which is equal to 1. Okay, so that's how you can determine whether or not something is a unit vector. All you have to do is find the magnitude of the vector, and if the magnitude of the vector is 1, then it is a unit vector. Now, there are what we call standard unit vectors. There are in particular two of them. One is I hat and one is j hat. So remember, with unit vectors, the way that we denote that vector is a unit vector, in other words, a vector of unit 1, is we use the little hat on top of the lowercase letter. So I hat is equal to 1, 0. J hat is equal to 0, 1. And these both have magnitude of 1, so you can double check, but in fact, the square root of 1 squared plus 0 squared is equal to 1, and the square root of 0 squared plus 1 squared is also equal to 1. So they do have magnitude of 1. Their directions are on the positive axes. So the I hat is going to be on the positive x-axis. Okay, so that's the direction of I hat. And then, as you can probably guess, j hat is going to be in the positive y-axis. So it's going to have the direction in the positive y-axis. So j hat's equal to 0, 1. You can see pretty clearly how that is in the positive y-axis. Now, another thing that we'll talk about in terms of notation, we can actually talk about unit vectors. Let's kind of use our knowledge of operations on vectors and see if we can rewrite using those, what we call standard unit vectors. So any vector v can be written as an expression in terms of the standard unit vectors. So let's say you have a vector v and it has components a and b. We can rewrite this, we can split it up so that we can write it as a, 0 plus 0, b, right? If we were to add those together, we'd get a, b. And then here we can take out an a, we can take out a b, so we end up with a outside of the vector components, and then 1, 0, plus b, take that out from the vector components, times 0, 1. Now, the 1, 0 and the 0, 1 now should look like the standard unit vectors that we just looked at, right? 1, 0, that's I hat, and 0, 1, that's j hat. So we have a times I hat plus b times j hat. So we can write any vector v with components a, b. We can write it as a, I hat plus b, j hat. So what we call this is linear combination form. Okay, so the vector v equals a, b in component form is now written in linear combination form. And we would say that the scalars a and b are the horizontal and vertical components of vector v. Okay, so let's do a very quick example. just to get ourselves used to writing a vector as a linear combination. So write vector v equals 2, 6 as a linear combination of vectors. Okay, so clearly you can see 2 is the horizontal component, 6 is the vertical component. So to write it as a linear combination of vectors, we would just have to put the 2 with the I hat and the 6 with the j hat. So we would write this as vector v equals 2 I hat plus 6 j hat. And that's it. All right, let's take a look at example 2. It says let vector v equal -3 I hat plus 8 j hat and vector w equal 2 I hat minus j hat. Find 2 times vector v minus 3 times vector w. Okay, so we're trying to find 2v minus 3w. We're going to go ahead and work with this in linear combination form. It's going to work pretty much the same as when we were working with operations on vectors. So vector v is -3 I hat plus 8 j hat. So we'll plug that in. Same with vector w is 2 I hat minus j hat. And then we'll just work with it just as we did before. So we'll go ahead and distribute that 2. So we'll have -6 I hat plus 16 j hat. And in the second parentheses, we have -6 I hat plus 3 j hat. And then we'll put together the like components. So -6i with -6i and 16j with 3j. So this ends up being -12 I hat plus 19 j hat. And there's nothing else we can do to combine that any further. So that's going to be our answer. All right, the next thing we're going to go over is how we can find a unit vector that has the same direction as any vector that's given to you. So say, for example, we have this vector here that's given to us. We don't know that it's a unit vector, but we do know it has components A and B. Now, if we're trying to find a vector in the same direction as the one given, but it's a unit vector, in other words, it has a magnitude of 1. So let's say that this is bigger, for example. Here's 1. So here's the unit circle here. So a unit vector would be one that goes out to the edge of this unit circle, but doesn't go any further. But we want to find the one that's in the same direction as it. So how do we find what that is? Well, we know the direction is the same as the direction of the given vector, a comma b. So what we need to do is we need to get rid of that magnitude, right? We need to change that magnitude to equal 1. Well, how do we take any number and get it equal to 1? We can divide by itself, right? We can divide. In this particular case, we don't want to get rid of the direction, so we're going to divide by the magnitude. Okay, so in order to find a unit vector with the same direction as a given vector, you will divide the vector by its magnitude. So, to write it as a rule, to find u hat with the same direction as vector v, u hat is equal to vector v divided by the magnitude of vector v. Okay, so we have talked about how you find the magnitude of a vector. So we just need to recall that and use that to divide the vector components each by that magnitude. So we'll do an example so you can see exactly how this works. All right, find a unit vector in the direction of vector v, which has components -2, 5, and verify that the result has a length of 1. So basically, find a unit vector, and then once you've done that, just check your work and make sure that it is in fact a unit vector. Okay, so let's write down the rule first. So u hat is equal to vector v divided by the magnitude of vector v. So let's go ahead and write down vector v is -2, 5, and then the magnitude, that's where you do the square root of -2 in parentheses squared plus 5 squared. And then we're going to go ahead and simplify the bottom as much as we can. So we have 4 plus 25, that's 29, so square root of 29. Okay, let's keep it as a square root of 29 because we don't, if we do mess with it a little bit, like try to find an approximation, then when we try to verify the result, it's not going to come out as exactly 1. So let's keep it as the square root of 29. So now you're just going to divide each component by the square root of 29. So negative 2 over square root of 29 and 5 over the square root of 29. You can leave it as is. You don't need to rationalize the denominator. That answer is fine. So now the next thing we need to do is to verify that this vector that we just found is in fact a unit vector. In other words, that it does in fact have a magnitude of 1. So we're just going to go ahead and find the magnitude of u, which is negative 2 over root 29, 5 over root 29. Find the magnitude of that, which means we are going to square each of those, add them together, and then take the square root. So we end up with 4 over 29 plus 25 over 29, which is equal to 29 over 29, which is equal to 1, and the square root of 1 is equal to 1. So we have, in fact, double-checked to make sure that this vector that we just found does have a magnitude of 1. Great. Let's continue. We'll relate this back to direction angles now. So if u hat is a unit vector such that theta is the direction angle, the terminal point, the head, lies on the unit circle, and you have u hat is equal to x comma y, and because it's on the unit circle, this is just going to be cosine theta sine theta. Or if you want to indicate the direction using your standard unit vectors, you can write this as cosine theta I hat sine theta j hat. Now consider a vector v that has the same direction as unit vector u. Then this vector is going to be equivalent to the magnitude of v times the unit vector u. Where is this coming from? This is actually exactly what we just did, except before what we just did was we divided the vector v by the magnitude of v to get the unit vector. Now, on the other hand, if you take the unit vector and you multiply it by the magnitude of v, then you end up with vector v, right? So we're just kind of rearranging this a little bit, but just note that what we have written right here is actually the same as the equation, the rule that we wrote down in order to figure out what the unit vector u is, right? If you were to divide both sides by the magnitude of v, that would give you the same equation here. So now we're just rearranging and saying that, well, if we're trying to find vector v, we multiply the unit vector by the magnitude of v, and that's how we can, that's another way of writing out a vector v. So we could say, well, then the magnitude of vector v times the unit vector, well, we just wrote down that the unit vector is cosine theta sine theta. And now if we multiply both of those individually by the magnitude of v, we have the magnitude of v times cosine theta, the magnitude of v times sine theta. And then if we want to write this in linear combination form, then we just write this as the magnitude of v cosine theta I hat plus the magnitude of v sine theta j hat. All right, last example. Find component form of vector v with theta equal to 115 degrees and the magnitude of v equaling 6. Okay, so let's write down exactly what we just wrote down in that last box. So vector v is equal to the magnitude of v times cosine theta, the magnitude of v times sine theta. We're told that the magnitude of v is 6, so we can replace that. And we know what theta is. Theta is 115. Now, you can absolutely do it this way. We can use 115 degrees. If you prefer to use reference angles, you can. Just know that when you use reference angles, that's when you need to take into account whether it's positive or negative depending on which quadrant you're in. However, if you use 115 and you plug that into the calculator, it's going to take care of the positive and negative signs for you. So you can think about this, theta equals 115 degrees. Think about which quadrant it's in, just to verify. And because it's in quadrant 2, we know that our x component is going to be negative and our y component is going to be positive. So then go ahead and plug this in. 6 times cosine 115 comes out to be negative 2.54. And 6 times sine of 115 is equal to positive 5.44, which is what we expect in terms of the negatives and positives, because if theta is 115 degrees, that must mean that it is in quadrant 2, and in quadrant 2, x is negative, y is positive. So if you do it this way, you'll get exactly with the correct positive and negative signs. If you use the reference angle, you do 180 minus 115 to get the reference angle, you'll end up with 2.54, 5.44, and then you'll just need to take into account, okay, I'm using a reference angle, and that's only for reference, so we need to determine whether things are positive or negative. And because we're in quadrant 2, you tack on the negative onto the x component. And that is it for today.